There you go.
And I was doing it.
Oh, yeah, big time.
Oh, you got, I got like the little shake. I don't really.
I was like, I don't think I would do anything wrong.
For trainer. Yeah, he's like. I would recommend that.
That's your problem.
Are you down? Yeah, we saw it times I didn't realize. I should have done.
Yeah, so someone's like. Psych out. I don't think my real only not. First week is so easy.
All right, it is 9:30, so we can start. Okay, first question. Raise your hand if you read the lab. All right, so we need to change this. You guys need to read the lab before the lab. So, yes, you still have time, but try and do it the day before because especially with the slides, I'm trying to help you with the lab. So it's good if you know what is in the lab so that I can help you more effectively. So do try and read the lab. Probably over the weekend is best because sometimes it's going to be split up between Monday and Wednesday where I'm helping you with the lab. All right, so we just need to finish up the slides from Monday, and then we can get into the slides where we're talking about the lab. So we ended with how we can implement subtraction with the same adder hardware, right? Because a plus negative b is a minus b, right? So the way that we're getting negative b here is we're just applying 2's complements. This is our bit flip. This is our carry-in of a 1. So that's how we add 1. Right? So we can use the same adder hardware to implement subtraction. And then if we don't want to make it a permanent change like this one is, right? Because this one, it's always flipping b. It's always negating, adding the carry 1. So it's always negating b, right? We can change it so that we can select if it's going to add or subtract. And the way that we select are with these multiplexers, right? So if we have 0, we're going to get the normal b, right? If we have 1, we'll get the inverted b. So based on this select signal, your poll, your code is 682. It's just, is this true or false? When select signal is 1, does addition occur or is it actually subtraction? Six, 8, 2. Is anyone still thinking about this? All right, so we are not at the threshold on just being able to move on from this. So do talk to people around you. Pay attention to the schematic. What is input into the adder when select is 1? What is input into it when select is 0?
Even if you're bad, it's.
I'm not trying to fool you this way.
I don't know.
Okay, I just want to clarify one thing real quick here. So in this schematic, your inputs are always A and then B, right? So if the result of S is A plus B, that's addition. If the result of S is A minus B, that's subtraction. Okay? Does that make it more clear for you? Yeah, question? Yeah, I will. Yeah. Yeah, so we keep moving back and forth between A and B. So we'll go through this together, all right? So basically you have two 4-bit inputs here, right? A and B. And they're of the form of 2's complement. So they're signed. So when we get the inputs A and B, and let's just say select is 0. So if select is 0, I do nothing to B, right? It's just B, right? And then select is also my carry in. So I don't have a carry in either. This is an adder, this is an adder, this is an adder, this is an adder, right? So it's just going to give me the 4-bit sum, which is now S is A plus B. Because B was not changed, right? But if select is 1, I invert all of B. And if I'm inverting all of B, that's the first step in negating it, right? Making it negative. And the second step is adding 1. So you add 1 with the carry in of 1. So now it becomes S is A plus negative B, which is A minus B. So when the select signal is 1, it's actually subtraction, not addition. Even though the hardware itself is always addition. Better for you?
Yeah, nice.
Okay.
I didn't take in the 1, so I just thought it was.
Oh, okay, I got
Yeah.
it. Yeah. Okay. So now we can move on to the lab portion of the lecture. So one of the parts of your lab is being able to display now multiple numbers with the display rather than just one. So you have this 4-bit number, and in this case, it's unsigned, right? So it goes from 0 to 15. So I can't display 0 through 15 with just one 7-segment display. I now need 2, right? But we saw in the previous lectures that I need to have this 7-bit code to tell me what number to display on the 7-segment display. So I can't just simply give it the 4 bits that represents the number in decimal, right? But representing it as binary and expect it to just work. I need to create some combinational logic to decipher with these 4 bits, what should my display be saying, right? So you will be given this piece by Mark. This is what we were implementing before, right? Just from the 4 bits and only expecting 1 digit out of it, what are the 7 segments that need to be activated? And the rest of this circuit, you're going to be implementing based on this truth table. Okay? So V is your input. So the digit that you want to display. So this is 0, 1, all the way to 9. So up until then, everything is normal, right? You just need this 7-segment decoder. But after 9, for 10, let's call this seg 0, seg 1. Seg 0 needs to be 0 when V is 10. Seg 1 needs to be 1. Right? So we can see that, right? M turns into 0. Then for 11, it turns into 1, all the way up to 15, where it turns into 5. Yes.
So basically, anytime anytime B is possible, and C is equal to 1,
Mhm.
and if you know what B is down.
Yep. Okay. So you can do this in this way, where you have a comparator, right? This would just be is if V is greater than or equal to 10, right? Then Z is 1, else Z is 0, right? But you don't have to do that. You can do it this way, or you can also just think about all of this all together as one circuit. Yes, question. Z is just the input into this circuit B. And all it is saying is if Z is 0, display 0. If Z is 1, display 1. Right? Because if V is 0 through 9, my seg 1 should be displaying 0. If it's 10 through 15, it should be displaying 1. Is it clear what V is now? Right. So for this, you can have it separated, but one thing that might be easier is just put it all into one component. Question.
Is it possible to Like just.
You would need to change this. So again, you don't have to do it exactly the way that I'm going to show you. It's just one way of doing it. I'm going to think about this whole thing as just one component that I just heard. And then all I have to do is case. And then, so when V is 0, then all I have to do is Z is 0, right? And M, which is going to be my input into seg0, is also just 0. Right? And I'm going to have 15 of these cases. I can go all the way down to when 1, 1, 1, 1. Right? So when it's 15, I need Z to be what? And I need M to be yes. So 0, 1, 0, 1. Question.
On a behavior model.
This is behavioral modeling. This top level circuit that you would be creating is structural modeling. Because you're going to instantiate all of these different components and connect them according to this diagram. Okay. So again, you also need to implement this circuit B. This circuit B is very simple, right? You can also do it with behavioral modeling. So if Z, which is going to be an input into it, is 0, then its output, I'm just going to call it out, you can call it whatever you want, is the 7, like, fine, okay, we can actually do it here. So 0, if we have 0, we need it to be 0. So everything except for 6. Oh, and it's actually reversed. Okay. 5, 6. Oh, wait, no. You need to test this, but it could be, it's either this way or this way. It's one way or the other. You need to figure out if the most significant bit is actually 6 or least significant bit is 6. I forget how it is in the lab on the board. Question.
So it's up to us to implement whatever model we want.
Mhm.
These are just examples.
Yeah, these are just examples. And then else out would be displaying 1, right? So if I want 1, then I need 1 and 2, right? So 0, 0, 0, 0. Yeah. 1 and 2. All right. So circuit B is fairly simple. This, if you want to implement it as the entirety of circuit A, it's also kind of simple. You just have more cases, right? But you can use behavioral modeling for both. And then you'll have another top level module where you're instantiating all of these components and connecting them together. Question. So it's the 7-bit binary outputs that tells the display which one of these to turn on. So, and if it's 0, it was on. If it's 1, it's off. So we have 0 through 6. So the topmost bit is off. So this one is off. Everything else is on. So it's displaying a 0. But for 1, I want only segment 1 and 2. So everything else is off except for 1 and 2.
Isn't that flipped what you just said? I thought 0 is on
You're right.
and 1 is off, so it should be all 1.
It should be all 1s except for 2 zeros. So 1, 2, 3, 4. Like that. And this should also be flipped. So 0, 1, 2, 3, 4, 5, 6. Yes.
And why is it flipped like that? Is that
Wait,
the
no.
nature of the?
I'm being silly. This one is right because all of them are on. 1, 2, 3, 4, 5, 6.
And that's just the nature of the circuit that.
It's just what this is expecting.
Oh.
Okay, is there any question on this still? This is enough to get you started? Yes? Okay. So the other part of it, I am providing most of, because you don't know specifically this. Because the way that the circuit is implemented, you can actually only display one number at a time. And the way that it actually looks like you're displaying multiple numbers at the same time is it switches which one is being displayed very, very fast. So that's what we're doing here. So we have this clock and we're keeping track of this count. And then once the count reaches a certain value, then we're going to reset it to 0 to restart counting. And then we're going to flip which digit we want to display. So that's how it's going to flip between it's displaying segment 0 or segment 1. Segment 0, segment 1. So this is how we flip it. So AN is the signal that is saying which segment to display. So there's 8 different segments. We're just only going to use 2 of them. So this is only displaying segment 0 because 0 is the one that is indicating that it's on. Right? And the 7 bits that we are sending it are from our segment 0 circuits. Yes.
So when it's going 0 to 6 on that, like, you know, the LED, we have like 0, 1, 2, 3, 4, 5, 6, 7.
Uh-huh.
So you're showing us the AN equals the quotations in 1, 1, 1, 1, 1, 1, 0. Is that going from left to right, following 0 to 6 on the LED?
No, so AN is 8 bits. It's not the same signal. Seg 0 is the signal that you're talking about. That is used to determine which of the 7 segments are on or off. AN is a different signal to determine which digit to display. And only one can be on at a time. So when we again get to this refresh count, we reset it and we flip which digit is displayed, then we'll flip to displaying the segment 1. So that is the digit that's being displayed. And the segments that should be driven by it are for segment 1.
In the 7 segment display, you can only just.
You can only display one digit at a time.
So you're just doing it really fast.
Yeah. Yeah. So you're just swapping between displaying the first one and the second one very, very fast. So I'm providing all of this code for you. You just need to write this into your top level module. And I'm also showing you how to connect part B to it, right? And also this piece to it. The only thing that I'm not showing you is the implementation of part B here because it's this thing, right? So there's a few different components to this part of the lab, but they're still relatively simple. And I think the main part that might be more difficult is just understanding what exactly is needed. So the question I have for you is it a little more clear about what these signals are expecting, why it's drawn this way, how things are supposed to be connected, and what is the purpose of this block? Okay. So that's one part of your lab. The other part of your lab are you're going to make some adders. So the basis for an adder is this half adder. You guys have seen half adders before, right? So it's just adding two bits together, then you have a sum and a carry. But we need to have more than just a half adder in order to implement a full adder, because sometimes you have a carry in, right? You have more than just these two bits. So your full adder is just two half adders connected to each other, right? This is one half adder. This is one half adder. This is an extra OR gate for the carry out. And they're kind of cascaded in this way, right? So the first half adder adds A and B together, and it has the carry if A and B are both 1. And then the second half adder takes the sum of A and B and adds C into it. And then also calculates if there's a carry because of this sum, and like the A and B sum and the carry. And then basically if either of these are a carry, you have a carry. So I'm going to go relatively quick through this full adder, half adder, because we've seen this before, yes? All right. So what you haven't seen before, though, is this structural modeling on how to actually make the full adder with these half adder components. So here is another example of this structural modeling. So we want to create this entity full adder, right? It takes A, B, C in, and you have a carry out, and you have a carry. We actually only need one of these. Only one of these is used. Yeah, so C is not used. Oh wait, no, it is used. All right, so I need to look at this again. But you have the two half adders. This one, so it's summing A and B, and the sum is going to AB sum. So it's an internal wire, AB sum. So if we go back to here, this is AB sum, that wire, right? And then the carry is AB carry, and that is right here. So AB carry with a C. So we see that how that is the first half adder, right? And then the second half adder takes an AB sum and C in. So that is here. And it outputs it to sum, which is C in this case. So this is C. I should rename it to S, but it's C. And then we have another intermediate signal, ABC in underscore C. That is this wire here, ABC in underscore C. And then this is our OR gate for the carry. So we see how we've mapped these two full half adders together to make one full adder. So I'm providing this as a template to follow, because your task in the lab is to then take full adders and connect them together to make a multi-bit adder. So here's your circuit diagram, right? So the first adder you're going to create is this ripple carry adder. So the key thing to note here is I calculate the sum for the first bits with the first full adder. I generate this carry, whether it's 0 or 1, right? And it goes into the carry in of the next adder. To calculate this one, goes into the carry in of the next adder, calculate this one, into the carry in of the next adder. I have my sum and my carry out. So your job is to create this by instantiating 4 full adders and connecting them appropriately. And you can use this as reference on how to connect things. Yes.
Is that effectively adding two?
Yes. Yeah. So it's adding 2 4-bit numbers here. And you'll be writing your test bench for this, testing it. So 4 bits, 2 inputs. You have many different combinations. It might not be very practical to test every single combination, right? So in this case, our best practice is, yes, do some normal tests, some edge case tests, right? So edge case tests would be like try making sure that you put in an overflow one. Maybe another edge case is just 0 plus 0, things like that. Okay. This part makes sense? Do you feel that you could make this, given that you are given this template?
They're not in the time about it for lab,
But over time,
but over time.
and you'll have Ford there, you'll have Mark there, you have Piazza if you need time outside to ask me. Right?
This
Yes.
is the beginning of the full adder, right?
What do you mean?
Or the code, because I was just trying to understand. Like I get the part where you're making the component and the architecture. And in the half adders, you're assigning to connect them together to move the wires, but how does it know to do like the different gates in the circuit above it?
Because the implementation is in the half adder. The half adder is the XOR gate and the AND gate. And then we add the OR gate. Right here. In the half adder, we go back here. It's an XOR gate and this AND gate, right? So this first one is the first half adder. The XOR gate, right? AND gate. This is the second half adder, XOR gate, AND gate. And then we add this OR gate right here. for this last OR gate. So this half adder, there is another file that is implementing this entity of half adder. That is the XOR gates. So it's A XOR B,
Oh,
and then
there's another file. That's
Yes,
what
yeah.
I'm confused about. Okay. That's all you need to do, so you have to write it.
I believe Mark is just giving you the full adder. So you don't even have to make the full adder. You make this file. But even then, it's 2 lines, right? A XOR B, and then A and B. If you needed to make that file, and then if you needed to make this file, it's right here for you. It's already made. Okay, so are we feeling better about this? Because you are going to make another adder. So the second adder that you are going to make is a more time efficient adder. So one of the downsides of this ripple carry adder is, like we saw with the combinational logic timing, the longest path defines how fast the circuit can be, right? So with this circuit, we have this pretty long path, right? I have to first go through this first full adder, then the second, then the third, then the fourth, until I can finally get my last answer. So this is very slow. Do we see why that is? Or sequentially calculating this, right? So that's where this adder is going to come in. This is a carry look ahead adder. So rather than waiting for this full adder to calculate what is its carry out and putting that into the carry in of the second full adder, we have all the information that we need in order to just pre-calculate if there's a carry for us or not. So that's what we're going to do in this circuit down here. We're going to calculate if there is a carry in for each of these bits not ahead of time, but in parallel. So we don't have to wait for the carry to ripple through all of them. So that's how this one is going to be faster. But as you can see, we have this whole new logic block. So this is faster, but larger. There's more gates in this. So we'll talk more about how to calculate these PNGs, their propagates and generates. But I just wanted to show you this other kind of adder that I think is also interesting. So in this case, we're trying to do 8-bit addition. So we have 4 bits down here and 4 bits up here. So rather than, again, doing just 8 full adders and rippling them all through, the way that this is doing it is it's splitting it up into 4 bits and 4 bits. The lower 4 bits, the top 4 bits. So the lower 4 bits, it's just going to do normally. We have our carry in, calculate the 4 bits, and we get a carry out. But rather than connecting that carry out into another full adder and doing ripple carry, what this circuit is doing is I'm not going to wait to figure out what the carry out of the first 4 bits are. I'm going to do the addition if there's a carry and if there's not. So this one is not a carry. This one, if there is a carry. And I have the result for if there is not a carry here, and if there is a carry here. I have them both. And then I'm just going to use this multiplexer with the actual results of the carry. So if there was a carry, I get this result. If there wasn't a carry, I get this result. So now I can do this 8-bit addition in the same time that I would do 4-bit addition, because this happens at the same time as this. But again, this is faster, but more, well, let's just call it larger, right? It's 50% larger than it needs to be, right? Plus some more because we have this multiplexer. Yeah, about twice as fast. Okay. So there are many other types of adders. I'm just showing you these two. You're not required to make this carry select adder. I just wanted to show it to you too. So the carry look ahead adder, you need this in order to do your lab. So we have this propagation and generation of carries. So propagate, if I'm propagating a carry, that means that I have a carry in, and I'm just then, because of this carry in, I'm propagating it to my carry out. If I did not have a carry in, I would not propagate it. So that means that for propagates, my bits, it's A or B, because if I have A as 1 or B as 1, then my carry out becomes my carry in. Right? So, and then to generate, that means from my 2 bits that are input at my, like if I'm the first bit, the way I generate a carry is if I have A and B as 1. So from my 2 bits, I'm generating a carry. So that's your propagate and generate. And then to get your equation for the carry overall, basically, I'm either going to generate a carry or I'm going to propagate from the previous one before me. And this would continue until the end. So you have this kind of recursive equation. So I have at my bit, am I generating or am I propagating from the previous one? Or I could also be propagating from a generation of the previous one, because I need to expand this equation from the previous one, which also has a generate and a propagate. So you only need to expand it up to 4 bits because you're just making a 4-bit carry look ahead adder. So you can model this in data flow if you want. That's what I would suggest because you have the equation here. You just need to expand it out. Make sense? All right, we have some time, so let's expand. Let's do the first equation. So carry at bit 0 is, so A of, let's do it. How do we want to do it? Yeah, let's A of 0 and B of 0. Or A at 0 or B at 0. This whole thing ANDed with CN. Right? That's our first carry for the first bit. Then if we want the second bit, we get A at 1 and B at 1 because this is the generate. Or I could be propagating, which is A at 1 or B at 1. And I need to AND it with the entire previous one. So A at 0, B at 0, or A at 0, or B at 0. And I ran out of space here, but C in. Yes.
Can we call that whole thing C of 0, or do we have to write out the whole previous one?
If you do it in data flow, you can create intermediate wires and just use those. Right, so like if you had this C0 as an intermediate wire, you can call this whole thing
It's a different signal.
would just be C0, right? But you can also just not do that and just have, they're not very, very long. So you would just have 4 things, right? So you have C0, C1, C2, C3. You only need to expand it out those times for the 4-bit. Right. And then here it's calling the carry in C0. So it's C1, 2, 3, 4. But do we see how to expand out this equation? So I did the first and the second one. You do the third and fourth one. I wouldn't do behavioral modeling. It would just write out the equation, right? So you just need to expand it out one more.
So 3 is going to be pretty long because it has to include the other 3 before it.
That's what I mean. It's recursive, right?
Yeah.
But it's still less gates than going through the whole ripple.
Yeah.
But there is a point where the carry look ahead adder doesn't become, it becomes impractical because of fan out. And fan out is how many inputs you're having into a gate. Because really these don't need to be just 2 input gates. They could be implemented as 3 input and things like that to simplify it. So usually you don't see carry look ahead being done more than 4 or 5 bits, but usually 4. And then if you want more speed, that's why you would do something like carry select. So you do carry look ahead 4 bits, carry look ahead 4 bits, carry look ahead 4 bits, and then carry select to make it again 2 times faster.
You said it was this is still less gates than the other one, but so it's just larger in the sense that it's a different component.
So it's less gates of longest path.
Oh.
But it's more gates overall, which is why it's larger.
Okay, that makes sense. So all the paths on this one are still shorter than the other one, okay, even though there's more components.
Mhm.
Okay.
Any other question? So the other thing that I should mention is that you can follow this also. Like if you make the 1-bit full adders, you can create the propagate generate signals and then have this separate logic block do the carry calculations. And it would be the same. So then you don't have to have very long equations. Like this just becomes generates this, so G of 0. This would just become P of 0, right? That's one way to kind of simplify it for you. But that's all of your lab for today. So it's first part of displaying multiple numbers, make the ripple carry adder, make the carry look ahead adder. Are we all good with being able to do this? Nice. Because we are out of time.
Answer anything on this question?
Just answer anything. So for the second question, just answer anything on Pull Everywhere.
What visuals to you? They give this example. Oh, that's familiar.
Yeah. I cannot look at Vivado.